Welcome to the Explainer. Today, we're tearing down the heady lifting heart of offshore drilling operations. We're going to see exactly how we bridge those massive mechanical demands on the drill floor to the macro electrical architecture that literally runs the show. If you're designing, commissioning, or operating these rigs, getting this power flow right is absolutely crucial. Okay, here's our roadmap for today. We'll hit the Drawworks challenge, check out the zero-speed solution, and then scale the whole thing up by comparing single versus multi-drive topologies before we weigh the final trade-offs. Let's get into it. Section 1. The Drawworks challenge, holding full load. So picture this scenario, one that would instantly stall out most traditional motors. You have to hold hundreds of tons of drill string perfectly still, at exactly 0 RPM for an extended period, without slipping a single inch. That's a totally routine Drawworks requirement. And it tells us right away that we're dealing fundamentally with a torque speed problem here, not just a raw strength problem. Moving to Section 2, the zero-speed solution, AC VSD technology. Now, what really changes the game here is that an AC variable speed drive, or VSD, delivers its full rated torque starting right at 0 speed. It holds that torque perfectly flat across the entire low-speed range. That's a massive departure from older motors that needed a minimum RPM just to wake up and develop full torque. Because on a Drawworks, a gap like that means drift or slip exactly when you need to be dead still. And we aren't just talking about a quick instantaneous burst either. This torque has to hold for extended stretches. Think about when you're making a connection or hanging in the slips just waiting on weather. The VSD has to keep pumping out that holding torque continuously without the motor burning up. It all boils down how expertly the drive manages current and cooling when the shaft isn't even turning. But the flip side of holding perfectly still is moving precisely slow. When you're tripping pipe in your bottom or trying to land a heavy string on a shoulder, you demand incredibly accurate low-speed control. At those slow creep speeds, a speed error of even a few percent could mean a catastrophic hard landing on the wellhead or the BOP. No one wants that. So, quick gut check to make sure we're grasping the real physical consequences of this electrical spec. Why exactly does a motor that only hits full torque above some minimum RPM fail as a Drawworks driver? Well, because the Drawworks routinely holds full load at exactly 0 speed, any gap in torque near 0 means your string is going to drift or slip. Coming into this explainer, you might have thought Drawworks performance was just about raw horsepower. Now you know it's really about 3 things: full torque delivered right at 0 speed, extended holding capability, and highly accurate low-speed control. And it takes some serious engineering to pull that off. You need robust, 0-speed capable hardware that gives you all that high-end holding and low-speed precision while being fully sealed up and armored against the absolutely brutal environment of an offshore rig. Section 3. Single versus multi-drive topologies. Powering the rig. Okay, you understand how one VSD drives one motor exceptionally well. Now let's tackle the broader architectural question. When you have several critical motors, do you give each one its own drive or share a big system between them? The contrast is pretty clear. With a single drive system, you've got fully independent converters, each with its own diode and inverter unit, feeding just one motor. But with a multi-drive layout, you have a single central supply unit, feeding a shared common DC bus that multiple independent inverters all tap into. So a single drive essentially gives you fully isolated failure modes. Every motor gets its own dedicated supply directly from the switchgear. A multi-drive setup flips that whole philosophy on its head. It uses one shared feeder serving multiple linked inverters, acting much more like an energy-linked ecosystem rather than a bunch of isolated islands. Section 4. The topology trade-off. Evaluating the options. Let's talk real-world constraints. Offshore rig space is some of the most expensive real estate on the planet, right? Because of that, the multi-drive setup very often wins the day on space, weight, and switchgear costs. Since they share a common supply, you end up installing far fewer heavy-duty breakers and pulling way less copper cabling compared to running a dedicated line for every single motor. But let's pause for a quick check. Think about how these individual units pull distorted current from the switchboard. Between the two, which topology do you think is going to require a harmonic filter on every individual drive unit? Yeah, it's the single drive. Because of its perfectly isolated nature, a single drive forces you to slap a harmonic filter onto every single independent unit. A multi-drive architecture, on the other hand, is super efficient here. It handles all that harmonic distortion just once, directly at the central supply unit.
And we see that exact same logic with regenerative energy. When you're braking, like lowering that massive drill string, that energy has got to go somewhere. Single drives force you to use individual braking resistors. Multi-drives just dump that regenerative energy right back onto the shared DC bus, tapping into one combined centralized braking resource for the whole rig.
Okay, but let's pressure test this against a critical failure scenario. Say you are designing redundant Drawworks drives. Safety and continuous operation are totally non-negotiable, and losing all your motors simultaneously is an absolute no-go. Which are you choosing, single or multi-drive? For critical redundancy, single drive isolation wins every single time. Here's why. In a multi-drive system, one central rectifier fault can easily cascade and drag all connected motors down at the same time. If you need absolute ironclad redundancy, you need the physical and electrical separation that only a single drive setup can give you. So this decision matrix really lays bare the harsh engineering reality we face. A multi-drive system easily wins on footprint, component count, and overall construction speed. But a single drive is just completely unmatched when we talk about absolute fault isolation and system redundancy. I'm going to leave you with this final provocative thought to chew on as you architect the power systems for your next commissioning project. The right call isn't about what looks best on a pristine spreadsheet. It all comes down to risk. Which failure mode can your specific rig design least afford? Thanks for joining me on this explainer, and I'll catch you in the next one.